Good morning. How have your 48 hours been? Okay. So Prince died. I was never a big Prince. I don't know. I always thought Prince was kind of weird, but I understand that he's made some significant, relevant contributions to music, and so I thought that we could play a Prince song today. So I was supposed to show everyone this chemistry club poster session thing. It's kind of late in the semester, I know, but also don't tell people that I'm showing like memes in my class. This is not my poster. So anyway, the chemistry club wants to offer help sessions, and I think that's cool. So Wednesdays 7 to 8, they'll be around. Yeah, I always love how 10 o'clock is congregated more towards its runs than 11 o'clock. And so if you guys were like an electron cloud, you'd be much. I mean, I were the nucleus. You'd be much more like an S orbital, whereas 11 o'clock is much more like a P orbital. They all go away. It's bad. Okay. Are we recording? So, I wanted to have maybe just a brief chat about that exam. Everyone remembers the exam from Wednesday. So I've gotten back some feedback. I've overheard some comments. There may have been some social media that mentioned the exam. I've got a pretty thick skin, so I can handle that. A little of it was slightly mean, but no, in reality, my wife had to come. I was like in my office breathing into a paper bag exam. So, all right. So I just wanted to have a quick chat with you guys about why do I teach? So, here's why I teach. I love to teach. It's not just a job for me. I'm passionate about this. I love doing this. There's a reason that I leave my wife and my mom at home on Easter Sunday to come talk chemistry stuff with you. I love this job, and I love helping out students. And part of the really cool thing about having big classes, because a lot of people don't like big classes, a lot of people want to be teaching small classes. I actually love the idea of teaching big classes because, let's see, I've got 150 people in this section. I don't think there's 150 people in here right now, but I've got 150 people in this section. So on average, let's say to make the math easy, you've had about 20 years of life experience as a group, right? And so 20 times 150, you'll have to help you out with the math. That's what? 3,000. Is it 3,000?
Yeah.
Okay, so 150 times 20 is 3,000. So that means that amongst all of you in this room, you have 3,000 years of life experience together, right, combined. That's actually a pretty fantastically large amount of life experience. That's going back to like King Tut when he was locked into his tomb in like 1300 BC almost, right? So this is a lot of life experience. So let's see. You're amazing, brilliant people, and let's say that you're going to have another 50 years from here to go do amazing things, whether that's perform surgery or litigate cases or write grant aids to help send money to the poor. And so 50 times 150 is what?
7,500.
Okay, you're smarter than I am.
7,500.
No, 7,500, I think.
7,500.
That's right.
Is that right?
7,500.
7,500. And so just this semester, just this class, I have a chance to maybe have the slightest impact on what will eventually be 7,500 years worth of good in humanity, right? And I think that's awesome. I love that. That's why I like my job. I get to know my students, and that's why I wanted this job first. Like, I had other job offers, right? And in a lot of other places, you're going to come, or you might experience one day, you're going to take classes, and people there don't love to teach. But I'd been at William & Mary, and I know the mission at William & Mary, and that's why I came back here. It wasn't just because of my alma mater. It's because I could come in here and actually form relationships with my students, and it's what I wanted. And so that's what I did. And so that's the good part of my job. And so here's the bad part of my job. The good part of my job is I get to know everyone. And I think I take more time than a lot of other professors to know people in my class. The bad part is I have to assess you. The school looks to me and it says, all right, you've got to give them a grade of some kind. And so if there's one thing I hate, it's giving tests of any kind. I hate it, but I get it. I get why it has to be done, right? We have to be able to assess our abilities somehow. And so you got to understand, when I'm grading an exam and I mark a problem wrong, I'm not cackling with glee whatsoever. What I'm actually feeling, and this is true, and it's serious, is I feel a little bit of anguish when I see someone not get a problem right. And especially if there's a problem that a lot of people aren't getting right. I feel really, really bad. And I think to myself, not, gosh, maybe they should have studied a little harder. I think going forward, what can I do differently, or what could I have done differently to have maybe helped them get that a little bit better? And so, one thing that I've had conversations with my colleagues where it's tough to write exams. The amount of organic chemistry stuff I know is like this. And the amount of stuff that I'm teaching you is about right here. And so what I've got to do is I've got to somehow gauge what's appropriate. Is the appropriate exam here, or is it here? And that can be really hard. I can shoot for a 75 average on an exam, but in reality, I have no idea where it's going to end up sometimes. I'm just guessing. And this early in my career, it can be a relatively difficult thing to guess with. So the exam, I think, maybe was a little too long, and the exam, I think, was maybe a little bit too difficult. But that said, William & Mary is a really good school, right? And so we can't have it both ways. We can't go to a tremendous, prestigious school and walk out of here and say, yeah, organic chemistry was not a big deal. Because then it's no longer a tremendous, prestigious school. It's supposed to be difficult. And ultimately, once we get past it, because again, a lot of you have not really been tested in your lives. You're all so freaking brilliant. You went to high school and a lot of you breezed through it, right? You did. You really did. And so now things get a little harder, and when I test you, it is meant to test you. It's not meant for you to have a box that you put a check mark in. It's meant to be a test. And so I've had, I don't know, how many students thus far in my career, 500, 600, 700, something like that. Not once have I ever had a comment or an anonymous evaluation that said something along the lines of, you know, I thought I did better than the grade I received. I'm pretty upfront that my classes will be curved and the grades will be distributed. If the exam average is a 50, and it won't be, but if the exam average were to be a 50, things will just get adjusted. If you did well on an exam where the average is a 50 and you got a 70, I mean, you kicked its ass pretty well in that case, all right? The whole point of this story is that, I guess at the end of the day, I'm on your side. I have your back. There's nothing I'm on board than for you guys to ace organic chemistry and roll forward into your careers with me having had some tiny little piece of influence in it. And so I just wanted to say that. There's always going to be a little I told my wife, I was like, so we saw some of the social media stuff, and I told her, I was like, man, this is what Sam Jones must feel like. I get it now. I think you guys are great, and while I'll always have a little bit of criticism, and that just comes with having such big classes, you know, I might have made it too tough, but I think you guys can handle it, and things will be curved appropriately. And I'm going to tell you already, that exam was chock full of partial credit. We've already got a lot of the spectroscopy problems. Not a lot of people got the spec problems, but a lot of people are getting 20 or 25 points on one of them. The other one, a lot of people are getting 15, 20 points. I think in general, more partial credit will be given out than not. So things are going to be fine. And honestly, with the way it's going to be graded, I think that the average is going to end up in the 70s right along with the other exams. So not a big deal at all. Okay. That's that. I have one other thing to talk about. And so this is actually really serious, and I take this very seriously. And that's the idea of fairness. And so people that took their exams in here, they had a pin on their board that said that the radical, or that the mechanism was not a radical mechanism. And so as far as I know, everyone else, at least in this section, had that information. Now, regardless of the details, it turns out that some people in the 11 o'clock section did not get that information. And that's not okay, because even if you could look at that mechanism and think that, yeah, sure, that's not a radical mechanism, it might have taken you 5 minutes to come up with that, and that's 5 minutes less that you had on your exam. And so ultimately, that's not fair. So I've had some conversations with my chair about how to best deal with this, and so I think I've come to a pretty good resolution for it. And so the grades, your score is going to be calculated two ways. And so the first way, it'll be with that problem, and the second way, it will be without that problem. And whichever's highest, that's what you're going to get. And so that gives me the opportunity to reward those who came in and aced that problem, and so you're going to get that credit, and you're going to get those points, and it'll help your score. And it's not a perfect solution, but it's sort of an imperfect situation, and that's how I think we can best deal with it going forward. Ultimately, it's not going to have a huge impact on scores at the end of the semester. So I just wanted everyone to know what was going on with that. Okay, any questions? All right, well, we've still got 4 classes of organic chemistry to go, and I'm still going to have lots of office hours and workshops and things going forward. We've just got to do like another 11 days and we're done with this semester, and so that's good stuff. All right. I didn't really script that, so it might have been a little wandering. So, today, I know, chatty. Oh, by the way, I was also told that I should just make a comment, and so I hear that I have one of the big lecture classes, and so on blowout, that can be a thing.
Yeah.
I'm just going to say a minor disruption is not a big deal. I cause minor disruptions in this class all the time. But ultimately, just know we are going to have material that is ultimately going to be somewhat important and relevant. I podcasted, it'll be available, but we do need to get it on, at least on the recording. So let's just try to avoid major disruptions of that kind if we can. Minor stuff is fine. I heard there's sometimes streakers. I don't know. Yeah, we'll have a big comprehensive final workshop. So our exam, I guess we should talk about it a little. Our exam is Tuesday evening. It's the second day of exams, and so that means we should probably try to have a workshop on that Sunday, a big comprehensive workshop. So I'll get those details out, and then I'll hold office hours all next week. So this can be, I mean, really, if you want to take advantage of it, you're going to have a week's worth of comprehensive review workshop type things before the exam. So there'll be lots of availability for that. Okay, so without further ado, I wish I had a joke to end that on. Okay, well, at least you still laugh a little, so. All right, so this is going to be Chapter 9, Part 2. And so this is going to be all about, we call it just elimination. We're going to call it beta elimination because it is a specific kind of elimination we are ultimately talking about, and that is beta elimination. Okay, so, yeah, I'm going to move on down on the paper a little bit. I need all the room. Okay, so we're going to say Roman numeral number 1. Intro. All right, and so let's talk about something we've seen already. So let's say we take a secondary alkyl chloride, such as this 2-chloropropane compound. And so let's react that with ethoxide. All right, now we've talked about what we would expect to happen in this case. We have secondary alkyl chloride. What do we want to do if we can do it? SN2. And so, can we do SN2 at a secondary alkyl chloride?
Yes.
We can. Do we have a good nucleophile? We do. And so, certainly, that is something that we might think about doing. All right, so of course, that would give us the substitution product. And so let's go ahead and say just the fact that we have a strong nucleophile is going to lead to a substitution reaction, and so specifically that's an SN2 substitution reaction. And so what we end up with on the other side will be this. And so that's something I think that we know at this point. So here's our substitution product. Of course, I think we'll also have some leftover chloride, but typically I don't expect you to draw an organic-y type leftover product, so I'm not too worried about it. That's not the only thing that can happen, though. And so in addition to ethoxide being a really strong nucleophile, what else is it? Is it an acid? It is not it's a strong base. And so what we're going to find is there's actually going to be two possibilities for the type of reaction that can take place with a given nucleophile or base. And so in this case, if we use it as a strong base, we're not going to follow a substitution reaction. We're going to do a beta elimination reaction. And so our beta elimination reaction, we're going to learn this mechanism specifically, just like SN2 is going to be E2. And so what do you think the 2 comes from? Bimolecular, right? It's the same thing here. And so in this case, we're going to have an elimination reaction where the rate determining step is a bimolecular process. And so that's why we have E2. And so in this case, what happens is we're still going to use our lone pair, but instead of going for the nucleophile, so let's define something really quickly. So let's say that the position that the chlorine is connected to, we're going to call it the alpha position. All right, so there's our alpha position. And so if that's the case, if we count one carbon away, what do you think we're going to call it? If we count one carbon away from the alpha carbon, what are we going to get? We're going to get the beta carbon. And so there's our beta carbon, and connected to that beta carbon, what do we have? We have a beta hydride, right? And so what we're going to do is we are going to eliminate that beta hydride. And so when we act as a base, it's that beta hydrogen that's going to be deprotonated. And so mechanistically, here's how our arrows go. So our base, we're going to start with our electrons, draw to the proton. And so we're essentially going to leave some electrons on this molecule. Now what's going to happen is those electrons, they're not going to end up as a lone pair. We're not going to have any charged intermediates in this reaction. They're going to quickly snap and form a double bond right there. Now, what's wrong with forming a double bond right there? How many bonds would this carbon be making?
5.
It'd be making 5. And so just like in an SN2 reaction where our leaving group leaves, guess what our leaving group does in an E2 reaction? It leaves. And so again, our leaving group is going to leave. So the product that we get in this case, we will have a new pi bond formed between our alpha and our beta position. And again, I guess we'll have some chloride left over. And so there's going to be two possibilities, and there's going to be two competing reactions as we dive further into elimination. We're going to see that not only, if we have a lone pair, not only can we do a substitution reaction, we can also do a beta elimination reaction. Josh?
So a pair of electrons go to the hydrogen in order to make it equal, because you can have 4 electrons on the hydrogen. The lone pair, the pair of electrons that binds the carbon to the hydrogen snaps and makes a pi bond.
Yeah, and so really all this is right here, this first part of the E2 mechanism is an acid-base reaction. We have an acidic proton, we have a basic thing here, and so this base is going to deprotonate this proton. And so since it's an acid-base reaction, the proton leaves its electrons, right? And so its electrons are going to stay with the carbon skeleton, but we're never going to have a lone pair or anything built up. And so instead of having just a lone pair, we're going to form a pi bond by kicking off the leaving group, just like an SN2 reaction. All right, so what we're going to find, and part of the complexity of this stuff is the fact that not only can, we've seen cases where there are multiple products possible, but in this case, we now are going to have multiple reactions possible. And so I'm going to boil this down and make it as simple as possible. We're always going to consider really one pathway to dominate, except in one special case that we'll spend time talking about, and it's not complex. Okay. So let's talk a little bit in Roman numeral number 2 about our concerted mechanism. And just like with an SN1, with the substitution reaction, we had SN2, we had SN1, also in elimination, in addition to E2, guess what else we're going to have? E1. We're also going to have E1, but again, E2 is better than E1. If it has a 1 in it, that's our worst case scenario. And so we're going to focus a big part of our time on E2, and so that's going to be our concerted elimination. And so just as a spoiler, that's our E2. It's got concerted mechanism, one step. So just so we're all on the same page, what we want to do is for our kinetics, letter A, we just are going to say there's only one step. And so if there's only one step, it's pretty easy to determine what the rate determining step is, right? It must be that one step that's occurring. And so since it's the rate determining step that tells us how fast our reaction is going to go, we're going to end up with a rate law that says the rate is equal to K. What's K? Some rate constant. We don't care really what it is. All right, and so we're going to have, we'll just say Rx. What is Rx?
Yeah.
It's just some alkyl halide, right? It's some R group connected to a halogen. So it's just any given alkyl halide. And so additionally, we're going to have our base. And so you can see that there are two things. And so here we have our bimolecular reaction. And so that's how we get our name, E2. Bimolecular. Where do you think the E comes from?
Elimination.
Yeah, that's just elimination. Okay, so that's fine. So that's our kinetics, and we're not going to go into too detailed of a look at the mechanism. What we're going to start focusing on is, all right, we've seen a case where we can have SN2 occur, or we can have E2 occur. So how do we determine which one's going to happen? And so we want to make some clear, defined rules for which reaction is going to happen. I don't want a lot of mixtures to be occurring with an SN2, E2 type substrate mix. So we're going to talk for a little bit about the competition with SN2, and so ultimately we're going to talk about all the cases that we can think about where one could win versus the other, and which one would win and why it would win. All right, so first off, let's just say that many strong bases are also strong nucleophiles, and so obviously a strong nucleophile is going to favor SN2. Strong base is going to favor E2. So we're going to have some way that we can tell these things apart. Now, are nucleophilicity and basicity the same thing? And we've highlighted the fact that one's a thermodynamic product or characteristic, one's a kinetic characteristic, and so they're different, and we can tell things apart. So that's going to make it possible. Okay, so the question we want to ask ourselves is going to be which reaction wins. Alright, so just like before, it's a little bit more general in this case, but just like before, what we want to say is if you can do SN2, do it. SN2 is typically the goal, right? But we're going to find some cases where we have to use some nuances to determine if we really can do SN2 or not. And so the way that we're going to classify this is by substrate type. So we're going to talk about methyl, primary, secondary, tertiary, and see the different situations where one reaction might predominate over the other reaction. So what we'll start off with is going to be a methyl alkyl halide. And so let's think about what a methyl alkyl halide looks like. So we use chlorine, but otherwise we have a lot of hydrogens. And so the thing about a methyl alkyl halide, and let's react it, we use sodium methoxide. And so could we ever do a beta elimination with a methyl alkyl halide? Are there any beta protons?
No.
There's not. And so with the methyl RX, there are no beta protons. And if there's no beta protons, we clearly aren't going to be able to do any elimination reaction. So what's always going to happen if we have a strong base and a strong nucleophile combined into one here with a methyl RX? SN2. It's just the only thing that can happen. And so what we'd end up with in this case is going to be our methoxide added. And there's really only one possibility in this case. And so anytime you see a methyl alkyl halide, you should know immediately that assuming there's a good nucleophile combined there, we're going to do SN2. E2 is just not a possibility because there's no beta protons. So that's actually a pretty easy case. So we're 1 down, 3 to go, and that one's pretty straightforward. All right, so next up what we're going to do is we'll take a look at primary alkyl halides. And so with a primary alkyl halide, let's see. So we're going to have two cases. So let's say that we're going to take this primary alkyl halide, and we were going to react it with sodium methoxide. And so then we're going to take the same alkyl halide, so we'll keep this here. And so now we're going to react it with sodium terp-butoxide. All right, now primary RXs in SN2 reactions, are they favorable for SN2? Yeah, and again, we're probably going to want to do SN2, but there are cases where we can discourage an SN2 and go the other route towards an E2. So that leads us to a new concept. We'll write in our notebooks, new concept. And so our new concept is going to be BBBs, is what we're going to call it. And so a BBB is a big, bulky base. All right, so those are our BBBs. And so what we're going to find is that if we have big, bulky bases, ultimately they're not going to be able to be very good nucleophiles. And so we can definitely talk about why that is. So if we draw out an idea of what a big, bulky base would be, so terp-butoxide as a base looks like this. And so you can see it's tertiary. Now we know that an SN2 reaction, the rate of that SN2 reaction is dependent on the crowdedness of the transition state. And so if this is going to be our nucleophile, this terp-butoxide, you think we're going to have a pretty crowded transition state? We're going to have a very crowded transition state. And so that's why the SN2 reaction is not going to happen with these really big, bulky bases. And so the BBBs is a way that we can discourage an SN2 reaction and actually just see the elimination reaction take place. Another big, bulky base that we can see is this diisopropyl amine compound. And again, we've got big, bulky groups connected to it, and the transition state for an SN2 reaction is just going to be too high for this to take place. And so what we find with our big, bulky bases is that they are awful nucleophiles. So that means we're not going to do SN2, so no SN2. But they're still amazing bases. And because they're still amazing bases, we can definitely encourage an E2 reaction in this case. And when we go back up to our comparison, we've got sodium methoxide in the top case. Can we do an SN2 reaction up here?
Yeah.
Yeah, we've got a primary alkyl chloride, we've got a really good nucleophile, and so primary alkyl halides are just going to want to do SN2 if possible. It's just not very high energy. So here, we would expect to see our substitution reaction. We would get this. And so what we can say is that the SN2 reaction in this case is really any time we're going to have a good nucleophile with a primary alkyl halide. If we have a good nucleophile, we want to look that route. But then in the other case, we have a big bulky base. Is that a good nucleophile?
No.
It is not, and so we can't do an SN2, and so in this case it's still really basic, so we can do an elimination reaction. Does a primary alkyl halide have a beta proton?
Yeah.
It does, right? And so it would be right here. Remember, we've got alpha, and then we've got beta. And so what we're going to do is elimination there. And so what we will end up seeing, I guess, is just ethylene, really simple pi bond. And again, that mechanism would look just like this. So we would end up with our alkene plus, well, we'll just worry about the organic product in this case. So here's one way that we can encourage elimination. So we're going to see our E2 mechanism prevalent. But we have to keep in mind that with primaries, it requires a big bulky base. And so we're halfway there. We've done methyls and primaries, and we've seen really what our possibilities are. Okay, so what do you think is up next? You would be correct. Okay, so next up, we're going to have our secondary alkyl halides, and so that's going to be secondary RX. And so this is where I'm sad to say it is kind of the tricky one. It's always the secondaries. Secondaries are always kind of the tricky one, and it's because they're just they're in that middle ground where they can do a lot of different things. Yeah. So the OT-butyl is just acting as a base, right? And so it's just doing this deprotonation, but otherwise it doesn't have anything to do with the resulting product. Yeah. And so everyone, I should maybe make this clear. This right here is OT-butyl. And so this is a terp-butyl group. It's one of those common names. And no one calls this, I guess, what would the actual name? It would be a 1,1-dimethyl ethyl alkoxide. No one's going to say that when you can just say terp-butyl. And so if you have this specific base where you've got essentially a tertiary carbon with methyls coming off of it, it's just going to be our tert-butyl group. Okay, so with secondary alkyl halides, let's see, so that's the tricky one. So I'm going to go ahead and just write the parameters down and we can sort it out after. So first off, to do an SN2 reaction, all right, so we're going to have something that can act as both a base and a nucleophile. So we'll just call that our base nucleophile thing. And so let's say that to do an SN2 reaction, we're going to have a base nucleophile. It's the same thing. We're just talking about different properties of that one thing. It has to have a conjugate acid with a pKa less than 11. All right, so we're going to have to talk a little bit about acid-base chemistry. And ultimately what it is if we have something, now let's think about what this means. If a conjugate acid has a pKa of less than 11, that means we're talking about stronger acids, right? Something like HCl has a pKa less than 11. And so that means if we had chloride that could act as either a base or a nucleophile, we know chloride's not very basic, so why would it do E2, right? If it's the conjugate of a very strong acid, it's not going to want to do E2 anyway because it's not a very good base. And so in those cases, we can prefer an SN2 reaction. So that means to do an E2 reaction, we want the alternative. We want things that not only are nucleophiles, but are also very strong bases. And in that case, if their conjugate has a pKa of greater than 11, we're going to find that they are basic enough to encourage an E2 reaction. All right, so again, we'll say the base nucleophile has a conjugate acid with pKa, in this case, greater than 11. So this one's a little bit tricky because now we have to think about some acid-base chemistry, which means we're going to have to take a look at some pKa tables whenever we're solving these problems. But in general, we're going to use a lot of the same stuff over again. So as we do the problems, we're going to get used to what the pKa of the conjugates are anyway. So you're not always going to have to look it up. And so for example, let's take a look at this secondary. All right, so we've got this 2-bromopropane. So we're going to react that with sodium iodide. All right, so is iodide a good nucleophile? Sure, iodide's a good nucleophile, but that's not the only thing that matters in this case. We've got to think about what kind of base is it as well. And so what's the conjugate of iodide? Yeah, the conjugate of iodide is going to be HI. And so what's the pKa of HI? It's very strong, right? It's around -9. And so what does that tell us about iodide? Is iodide going to be a strong base that prefers to go E2, or is it going to be just a great nucleophile that goes SN2? It's going to go SN2, right? And so here, we would expect our SN2 product to occur, and that's exactly what happens. So we just get substitution. We kick off our bromine, we end up with our iodide in place. And so what we can say is that we're going to go SN2 in these cases where we have a relatively weak base. And so that's ultimately what that pKa of 11 kind of guideline is. And that's still ultimately just kind of a guess of where the line is. But we're going to say that in this class, if 11's a hard, dead rule that always works. And so we're just, if it's above 11 or below 11, it's going to get one reactivity or the other. All right, it does get trickier in real life. Because again, basicity and nucleophilicity are different things, and so. All right, so alternatively, what we can do is we can pretend to treat it with sodium methoxide. Now, what is the conjugate acid of methoxide? Well, what is methoxide? Methoxide is OMe with a minus. Its conjugate acid is going to be the protonated form, and what is that? Yeah, that's methanol. And so what we've got to know is the pKa of methanol, and so we could look up really just the generic pKa of any alcohol, and we would find that pKa is going to be around 17. All right, so now that we know that about the conjugate acid, when we look at sodium methoxide, is that going to be a strong base or a weak base? It's going to be a strong base, and so here's where it gets a little bit tricky, because in the past, what we've done in this case is we've just done the SN2 reaction, right? If we could do it, we would do it. But now we see there's a little further nuance. Methoxide is certainly a good nucleophile, but more importantly, it is a really, really strong base. And so in this case, what are we going to favor? Now we're going to be doing E2 anytime we see methoxide. Specifically, with what kind of alkyl halide? Secondary. And remember, we're seeing different reactivities. Up here, when we had sodium methoxide, we saw that we actually did an SN2 reaction. But once we move up to a more sterically hindered secondary, the reactivity changes a little bit. And so that's why I'm trying to have these clear-cut boxes right here that are telling us with each kind of substrate what kind of reactivity we would expect. All right, so in this case, with a secondary alkyl halide, we're going to find that we do the E2 reaction. And so we end up with that product. And so we do E2 because, well, now not only do we have a strong nucleophile, we also have a strong base, and that's just going to be more important with secondary alkyl halides. Yeah?
Does it matter what side the little bond?
In this case, it doesn't because it would be the same. It would be the same molecule. But we're going to get into some regiochemistry and some stereochemistry ideas for elimination. We might not get to that until Monday. Okay, so that leaves tertiary. And so tertiary is actually pretty easy again. So tertiary. Can we do an SN2 reaction at a tertiary alkyl halide? We can. And so just right off the bat, no SN2 allowed. So really there's only two things to remember because we've seen now that with methyl alkyl halides, there's no elimination allowed. And so then at tertiary alkyl halides, there's no SN2 allowed just because it's too crowded. We already know that. So pretty much anytime we have a tertiary alkyl halide such as this, in this case, we can treat it with, again, sodium methoxide. Is sodium methoxide a good nucleophile? Yeah. It is, but we can't even consider SN2 in this case because it's tertiary. So then we just think, all right, what else can we do? Is it a strong base?
Yes.
It is, and so what we're going to end up doing is a beta elimination. So we find our beta hydride, go ahead and eliminate it as such. And so what we'd end up with in this case would be this product. So pretty much we'll just say that E2 will occur anytime that we have a strong base. And you know, really, it might be a decent idea that in your own time to maybe write down, you know, all this stuff on one page, just these boxes. So for primary, if you have this, it'll do one thing. If you do this, it'll do other thing. And it might be a nice little cheat sheet as you go forward studying. Okay, I lied. We're going to get to regioselectivity. Here we are. Any questions about that? That's 4 different kinds of substrates now that we've seen can do different things based on the nature of the base of the nucleophile. Yeah, it could be. So we're going to find in some cases, for right now, yeah, you can look at the beta hydride as you get imagine. Yeah. Yeah, so what we're going to find is if the reaction mechanism has a 2 in it, if we can do one of those, we're going to do it. So we're only going to start considering SN1 and E1 stuff as a last resort. And ultimately, it sounds complicated, but it's not. So once we start having the possibility to do SN1 or E1, what we ultimately find is they both occur and you get lots of complex things. But the nice thing is that you don't actually have to pick one over the other, because you're just always going to know that once you start forming carbocations, either thing can take place. But we'll talk about that maybe Monday. All right, so now we'll talk a little bit about regioselectivity. And so these reactions are regioselective, and so we haven't seen a case yet, but we can come up with something. So let's say that we use this secondary alkyl halide. And so let's see. We can do SN2 depending on what the pK of the conjugate is. And what I want to do is elimination. So I'm going to choose hydroxide. What's the conjugate of hydroxide?
Water.
Yeah, so the conjugate is water. What's the pK of water? It's about 15.7. And so is that going to prefer to do SN2 or E2? E2, because it is a strong base with a conjugate of a pKa higher than 11. And so we can do E2 in this case, but now we see that, well, we have a beta hydride here, as well as a beta hydride here. And so depending on which one we eliminate, we're going to see that we get different products. So if we eliminate the one on the left, we'll end up with that product. If we eliminate the one on the right, we're going to end up with that product. All right, so we'll talk about stereochemistry in a little bit. Yeah, this is trans, cis is possible, but we're just worried right now about the different regio products that we can get. All right, so there's two regiochemical outcomes in this case. We can have the internal alkene, or we can have the terminal alkene. And so what we're just going to go ahead and say, do I have that right? I have it written differently in my notes. Yeah, that's fine. And so what we're going to say is that this we refer to on the right as the Zaitsev product. I know. Markovnikov, Zaitsev, yeah. All right, and so that's the Zaitsev product. So who wants to know what Zaitsev's rule is? I do. Yeah, we all do. Okay. So let's go ahead and talk about Zaitsev's rule. And so in Zaitsev's rule, basically it says that E2 reactions, and so specifically it says E2 reactions with unhindered bases. And really we should say unhindered strong bases, because we need a strong base to do any kind of E2 reaction. So reactions with unhindered strong bases favor the more substituted which actually seems a little weird, and we'll talk about what it is. But basically, the more substituted alkene, meaning the alkene with more carbon stuff coming off of it, is going to be the more stable product, and therefore the Zaitsev product. So we see our Zaitsev product over here. How many R groups do we have coming off of the alkene? We two, right? We have this one here and this one here, and so we would call this a disubstituted alkene. Over here on the left side, how many R groups do we have coming off? One. Just the one, and so here we have a mono-substituted alkene. And so what we're going to find is since this is the Zaitsev product, and we certainly used an unhindered base in hydroxide, we're going to end up with a major product of Zaitsev, and then a minor product of, it's technically called the Hoffman product, but we're not going to worry about it. So just the minor product in this case is the less substituted product. All right, so why, I guess, do you think a disubstituted alkene is going to be more stable than a monosubstituted alkene? Does anyone wonder why? Why? Yeah, so what we're going to find is we can make this trend of alkene stabilities, and so we'll say, why? Just like and this is the easy way to remember this, just like carbocations are stabilized by substitution, so are alkenes. And honestly, it's for similar reasons. So carbocations are stabilized by carbons through just an electron donating effect as well as a hyperconjugative effect. It's the same thing with alkenes. Having carbons on there, it donates electrons to the pi bond, it stabilizes it, and there's also a hyperconjugative effect. So it's pretty much the same reason that carbocations are stabilized. What that means is that if we have increasing energy here, ethylene is going to be our least stable alkene, and then as we go down in energy, and so we increase our stability, we see we have our monosubstituted. Then we hit our disubstituted. And so what we're going to find is we have two possibilities. So we can have cis or trans. And so between cis or trans, why do you think trans is more stable than cis? It's a steric strain thing, right? And so we have R groups on the same side. That's going to give some steric strain to our pi bond or to our alkene. And so we're going to find that it's a little more stable to have the trans double bond. But then, interestingly enough, the more we substitute this thing, the more and more stable it gets. And so ultimately, at the bottom, we find that our tetra-substituted alkene, even though it's, I mean, you would think that it's very sterically hindered, and I guess it is, but the fact that there is stabilization for pi bond just overcomes the steric hindrance, and so we end up with this being our most stable. Here we can say that trans more stable than cis due to sterics. So sterics only really come into play when we have the di-substituted cis-trans possibility. Otherwise, it's all about substitution. Okay, so that's pretty much it on regiochemistry. If you ever have two possibilities to undergo our elimination, think about which products you can form, and so it's just going to be the more substituted product, the Zaitsev product, that's going to be favored. And ultimately, that one is favored because it's just, we end up with a more stable product. Now, does the energy of the product really affect the reaction rate? It's the activation energy, right? The transition state. It just turns out that the transition state has a lot of pi bond characteristic, and so that's why it typically mirrors the product in this case. I didn't want to draw that out and deal with all that stuff. Okay. We got a few minutes. We'll go ahead to D. So this is going to be stereoselectivity. So really, I'm just gonna write down and make one point here, and then we'll call it a day. So what I want to highlight is that E2 reactions require, and so this is absolute. I don't say a lot of absolutes, I feel like, in this class sometimes, but in this case, we're definitely going to have an absolute. So E2 reactions require the beta hydrogen to be anti-coplanar. And so what anti-coplanar means is that it must be 180 degrees from the leaving group. And so we can maybe most easily picture this through a Newman projection. So if we have some Newman projection, let's say we have a hydrogen straight down and our leaving group straight up. Is our hydrogen here, is it a beta hydrogen compared to our leaving group? Yeah, it's 2 carbons away. Is it 180 degrees from our leaving group? Yeah. It is. And so this is the orientation that our hydrogen must be. It must be on the other side, exactly 180 degrees from the leaving group. And we'll do some examples of that next time where we see where it matters. Because ultimately, we're going to find that sometimes the cis product can be the only product, or the trans product can be the only product. It's going to be based on making sure we're in this configuration. All right, have a good weekend.
I liked your talk.
Huh?
I liked your talk.
Thank you. Yeah.
Yeah.
Felt like it needed to be said.
Yeah. Yeah, I felt like that too. Do you think I can get in the car over the weekend?
Yeah. I'll probably. This is gonna be a longer day for me. I'll probably be here at least past till like 4.
All right.
So I'll just. Is there some time you need to be gone?
Not after like 4-ish.
Okay.
Not until like 8. I mean, if
Right.
you're
I
not
won't be
staying.
here till 8. So yeah, I'll shoot you a text once I think I have a better
We
idea.
can also talk about like.
Yeah.
research
And
stuff.
Jonathan came down actually, and he thanked me for sending you along. So I think you honestly have got a really good chance. It means a lot to get a recommendation from a colleague.
Right.
So yeah, I think you got a really good shot.
All right.
Yeah.
I'll see you later then.
I see it.
Okay, question.
Yeah.
For the rest of the year, are we gonna be, it says on the syllabus we're covering chapter 7, are we still gonna do that?
We'll do a little bit of it, maybe. Just a bit. It's not the most important topic in the world, so, and a lot of it honestly ends up being review of alkenes. Because what it is, chapter 7 is alkynes, which for the most part have very similar reactivity to alkenes. Alkynes can do pretty much the same electrical recognition reactions that alkenes can do.
So should we read the
I
chapter?
would read the whole chapter. Let's wait and see how far we get.
Okay, but we're not gonna be doing it on Monday then?
No, we'll do elimination probably all the way through Wednesday.
Oh, so it might just be like chapter 7 then?
It would probably be like that.
Okay, and And then is there a workshop on Sunday or no? Because like we just started.
Not this Sunday. I think I need a weekend off.
Yeah, I mean there's not really anything to do.
Yeah, I think we'll crank it back up on Monday, and then we'll go heavy into it.
Thank you. Have a good weekend.
Yeah, you too.
And a quick question about, I think I'd written down that for SN2 you needed a strong base, or like strong base favored SN2.
So up until now, we haven't really talked too much about the differences between basicity and nucleophile. We've said that you can often determine that something's a good nucleophile if it's also a good base. But they're different things and they don't always line up. So what we're seeing now is we're actually drawing the line in the sand, saying where something, even though it is a good nucleophile, where basis is just more important. And so now that we understand the elimination reaction, we can determine when the elimination will take place, and it's based on that conjugate pKa of 11.
I thought I had written down in class that like a strong base with a pKa greater than 11 would favor an SN2 from previous class.
So what it is it can often be, and again, it's because we didn't know the whole picture.
Right.
But now we're basically now clarifying. So some of it, like before, we've used methoxide as a nucleophile in all cases, right? But now we're seeing that the rules don't always hold up because it's actually a very good base as well.
Okay.
And so now we've got to consider other things. My goal is that we'll have a nice, clean chart put together at the end where we can know exactly what's going on.
Okay, that would be helpful. Like I plan on making one of those, but
Yeah.
if you happen to have